Now let us learn what is called as skew lines. In three-dimensional space, if two lines are such that they are neither parallel nor intersecting, then they are called as non-coplanar or skew lines. Now we are aware that in two-dimensional space, if we have two lines, then they must be either parallel to each other or intersecting each other, right? There is no third possibility. But here in three-dimensional space, there is a third possibility also, and that is what is called as skew lines or non-coplanar lines. Now as an example of like how the skew lines might look like or where they might be located, let us consider a box, okay, a box like shape. I'm showing the edges which are behind, we can't see in dotted line. Now let's consider a line which is lying on the topmost face of the box like this, and let's consider another line which is lying in the lower flat face of that particular box. Now if you look at these two lines, we can immediately see that they are not parallel to each other. On the other hand, they are also not intersecting because the two faces, the one which is at the top and one which is below, they are two parallel planes, isn't it? So they will never intersect also. So hence these are the lines which are neither parallel nor intersecting, and hence they are called as skew lines. Right. Now let us derive a formula of how to find the shortest distance between the two skew lines. Right. So here the example shows that we have a first line having a given point and a vector to which the line is parallel, and we have a second line having a given point and a vector to which that second line is parallel. Now the segment PQ is the segment of shortest distance between the two skew lines, and we note that that segment must be perpendicular to both of these lines simultaneously, and we have to find the length PQ. Right? Now for this we do one small construction like this. You see, from point P we are going to draw a parallel segment to the second line, the one which is below, and from B we are going to draw a segment parallel to PQ, and it will intersect the previously drawn segment in, say, point R. Let it intersect in point R. Now we join point R and A. Okay. We also join point B and A. Now from point P, let us draw a parallel line to RA, and from A let us draw a parallel line to PR, and those two lines, let them intersect at some point, say S. Okay. Now there will be of course one edge which is behind, which is not seen, and that edge is QS. So if we draw that edge, it will look like this. Okay. So you can imagine a 3D solid figure in front of you. Now if you observe the angle ARB, this particular angle has to be a right angle, correct? So therefore if you look at triangle ARB from right side, in the direction as shown here, it will look like this. So here we have A, perpendicular right angle, R, and the lower vertex is B. So clearly this particular edge, the hypotenuse, can be written as A bar minus B bar. You can write it as B bar minus A bar also, but for the derivation it doesn't matter. You can take any order which you want. Now if you observe that length PQ is same as length BR, isn't it? So therefore it is sufficient to calculate length BR, which is nothing but the required shortest distance. Now if you observe, length BR is nothing but the projection of A bar minus B bar in the direction where BR lies. Okay. So the direction in which BR lies is like this, isn't it? It is along the vertical direction as shown in the figure. That means to get that projection, we must get some vector in this particular direction so that we can get the projection of A bar minus B bar. Now let's think which is that vector we can easily find out which lies in this particular direction. For that we have to look at the two given vectors, that is b1 and b2. Right? If we take the cross product of b1 and b2, then definitely b1 cross b2 will lie in the required direction, because the cross product is always perpendicular to both of the vectors whose cross product is being taken. Okay? So therefore from the figure it is clear that the cross product will be perpendicular to both the lines. That means it will be perpendicular to b1 and b2 also. Right? So that means projection of a bar minus b bar on the vector b1 cross b2. Okay? This is the required shortest distance, and by formula we know that the projection of one vector on the other vector is the dot product of two vectors, that is a bar minus b bar dot b1 cross b2 whole divided by modulus of that vector on which the projection is being taken. That means magnitude of b1 cross b2. Right. And since the whole quantity represents the distance, that has to be a positive number, therefore at the end we take the absolute value of the entire answer. So this is the formula to remember. Of course, this formula can also be remembered in a different way, or rather by simplified manner. That is, the first row is x1 minus x2, y1 minus y2 and z1 minus z2. Okay, because it is the subtraction of coordinates of a bar and b bar. Second row is comprising of the direction ratios of b1 bar. So let them call as a1, b1, c1. And the third row is nothing but the direction ratios a2, b2, c2 of the second vector, that is b2 bar. And divided by the magnitude of cross product will be nothing but, you see that in the cross product the second and third row will remain same. It's just that the first row will be nothing but I cap, j cap and k cap. So the magnitude of that cross product can be calculated as b1 c2 minus b2 c1 the whole square plus a1 c2 minus a2 c1 the whole square, and lastly a1 b2 plus a2 b1 the whole square. So in this way we can calculate the shortest distance between two given lines. So remember, the first form is better because that is shorter to remember, and ultimately when we substitute the value we are going to get anyways the second form on expansion. Yes. Now let us solve one example based on this formula. Find the shortest distance between the lines. We are given the equations of two lines. Right? So here the first line has the given point a bar, which is nothing but 4i minus j. So we write that 4i minus j. Then b1 bar is the vector to which the first line is parallel. So therefore that turns out to be I cap plus 2j cap minus 3k cap. And similarly for the second line, the fixed point on it is b bar, which is I cap minus j cap plus 2k cap. And the vector to which it is parallel is b2 bar, that is I plus 4j minus 5k. So let us first calculate a bar minus b bar. A bar minus b bar is the corresponding subtraction. So we get 3i, 4 minus 1 is 3i. Then minus j, minus of minus j is 0, and we have minus 2k. So we get first input a bar minus b bar. Now we have to also calculate b1 cross b2. We have to get the cross product of b1 and b2, and we know that that is given by I cap, j cap, k cap. Okay, B1 is 1, 2, minus 3 and B2 is 1, 4, minus 5. So that turns out to be minus 10 plus 12, that is 2i, minus 5 plus 3, that is minus 2, that will make it plus 2j, and lastly you have 4 minus 2, that is plus 2k. So we got the cross product also. Let us calculate its magnitude here itself. So the magnitude of cross product B1 cross B2 is equal to, since all the components are same, 2 square plus 2 square plus 2 square, that is 4 3 are 12, and that is nothing but 2 root 3, and therefore the shortest distance, if you call it as say D, then as per the formula we have to take the dot product of these two vectors, that is a bar minus b bar and b1 cross b2. So that turns out to be 3 into 2, that is 6. Then the product of j coefficients will be 0 because in the first vector j cap part is missing, and the product of k cap will be 2 into minus 2, so that is minus 4, that is 6 minus 4, whole divided by magnitude of b1 cross b2, which we just found to be equal to 2 root 3. So therefore in the numerator we have 2, and 2 divided by 2 root 3, so the 2 will get cancelled and we will get the final answer as 1 upon root 3. So that's the shortest distance between two given skew lines.